Okay, let's go ahead and get started. Today we're going to cover something new. The midterms should all be back. We went over that, so we're going to start something new. And specifically what we're going to do is before the midterm we talked about regular languages versus non-regular languages. And we had actually found that non-regular languages exist. And not only that, we even proved that that language A to the N, B to the N was non-regular. And that was a really simple language. So as a reminder there, the language is A to the N, B to the N, so the same number of A's as B's. And that's not a regular language. And notice how simple that language is. It's really easy to understand. It doesn't require some really complicated, convoluted thing to have this language be non-regular. So in other words, it's just a string with a number of A's followed by the same number of B's. That's non-regular, meaning that we could never make a DFA, an NFA, or a regular expression for it. And so to represent a language like that, we need something more powerful, or something different. So we need a formal way to represent a language like that even though in this case it's relatively simple, DFA, NFA, regular expression could not do that. So we want to create something. So we need a formal method that can represent all of the regular languages and then also represent some additional languages like this one up here that are not regular. And the solution to that is what's called a grammar. Now, a grammar, the formal definition of that, it consists of 4 parts. And those 4 parts, it's a quadruple, so V, T, S, and P. And V is a finite, non-empty set of objects called variables. So that's just a set, has to be finite, has to have at least one thing in it, but that's variables. T is a finite, non-empty set of objects called terminals. And to put this into perspective or into relation with DFAs, T is essentially our alphabet. That would be sigma that we had before. So T, but we're going to call them terminals here and use T rather than sigma like we used before. S is a single special variable called a start variable, and S has to be an element of V. So in other words, V has to have at least one symbol, and S is the defined start variable for that grammar. And then P is a finite non-empty set of productions in the form X. This is read X produces Y, where X, it has to have at least one variable or terminal in it. Could have a string of them. And then it's producing this thing on the right-hand side that is 0 or more variables or terminals. So V union T star on the right-hand side, on the left-hand side, V union T plus. So in other words, what this production does is it's basically allowing it to take one string and replace that with another one, which that one could have some part of a production, which could then be replaced by another one and another one. And we're going to build up a string that way. So a lot like a DFA, as it walks across those edges, it kind of builds up the string, or you can think of it as matching parts of that string. This is kind of similar, except that we're replacing this thing with that. And that's why it's called a production. This produces that. This gets cut, and this gets pasted in place of it. Now, a quick thing to note is that notice that this is still a finite thing that we have in this grammar. Notice that all of these parts are finite. V is finite, T is finite, P is finite, and S is a special variable called the start variable, single variable. So there's nothing infinite about this. Where to solve this language that we had back here, we could not make a finite state machine that solved that, but we're going to be able to make a grammar that solves that. And it's finite. It's just a different kind of mechanism. Now let's look at the rules for how the grammar works. And essentially it works like this. We start with the defined start variable S. And then we find a production that has S on the left-hand side and only S on the left-hand side. And then we replace that with whatever's on the right-hand side of that production. So again, we cut S out, cut the left-hand side out, replace it with whatever's on the right-hand side. And that makes a new string of things. And then from that, we now find a substring that matches the left-hand side of some production that's defined in our set of productions P. And if we find a left-hand side that matches some substring, we cut that and paste that. And we essentially repeat that process until what we end up with is a string of only terminals, or a string that's an element of T star. Only terminals allowed in that, or lambda. Lambda could be in there as well. But only terminals or nothing. So no more variables left, and that string now is just entirely symbols from our alphabet, so that string is in the language. So the definition in this case is of the languages defined by grammar is the set of all strings in T star that can be generated by starting with S. So if we can start with S and generate that string is in the language, and the language defined by it is a set of all strings that we could generate by starting with S. Okay, now there are a couple sub-classifications of those grammars that are important for us, and we're going to focus on those right now. So notice we didn't do an example of this yet. We'll do an example of these kind of grammars later, but I want to focus on these kind of subset or restrictions on those. So the subsets or classifications of these grammars that we're going to focus on are context-free grammars, regular grammars, left linear grammars, and right linear grammars. And note that those are really just restricted forms of the grammar that we defined earlier, a restricted form of this. And specifically what gets restricted is going to be how we create these productions in P, the elements of P. All right, so let's look at that. So restrictions on the elements of P. Let's start off with context-free grammars. And a context-free grammar, or a grammar is considered context-free if all the productions are in this restricted form where we have A producing X. And in this case, A has to be a single variable, and X is V union T star. So notice that what this restricted was that the right-hand side was the same as what we had before. This was V union T star before. And let me back up and show that here for a second. See, this was Y, in this case it was Y on this side, but it's whatever the right-hand side was an element of V union T star. But the difference now is the left-hand side, we have restricted it to only having a single variable. So the left-hand side of the production is just a single variable, and that's it. And that is going to be useful for us because it's going to simplify the replacements in such a way that the context of how the variable uses and the symbols around it don't matter. It's just a single variable on the left-hand side being replaced by some string of 0 or more, potentially 0 or more variables and terminals on the right-hand side. So that's the restriction, but so we're always going to be replacing a single variable with a string of variables and terminals. And hold on one second. Okay, so this simplified form is going to make it easier because we're only replacing one thing. In other words, context isn't going to matter. It doesn't matter how the variable is used or the symbols around it. We're just going to say, if I see that variable in my string, I can replace it with whatever this is on the right-hand side. Now, a couple other definitions. A regular grammar is, all regular grammars are also context-free grammars, as we'll see in a second. But a regular grammar is one that is either entirely right linear or left linear. That should say or. Let me fix it. All right, so it's either right linear or it's left linear. Well, now we need to define those. So what is a right linear grammar? It's one where all the productions are of the form single variable produces a string of terminals followed by a single variable, or a single variable producing just a string of terminals. So notice that this is a further restriction on context-free, which means that all right linear grammars are also context-free grammars because there's always a single variable on the left-hand side. So a right linear grammar has imposed a restriction on the right-hand side, not the left-hand side. And in this case, notice we have a string of variables, or a string of terminals here, and always a single variable at the end. We're not allowed to have more than one variable on the right-hand side. It's either no variables and just terminals, or a string of terminals followed by a variable. And left linear, as you can guess, is the same concept, except for a left linear grammar, it's always a single variable producing a single variable followed by a string of terminals, or a single variable producing it. So in other words, we've just switched the variable to being from being at the end. We've moved it and pushed it up to being at the beginning. So a question here, are all regular grammars context-free? Yes, because even though we've further restricted the right-hand side, the left-hand side still has just a single variable. So all regular grammars are also context-free, but all context-free grammars are not necessarily regular grammars. So moving on, well, there's our answer. We already answered it, yes. A little bit of lack of drama in that bold-faced thing down there. Now, the thing about regular grammars, as you can imagine, they can only represent regular languages. So in other words, if I have a grammar, a context-free grammar that's in this form or in this form, all the productions look like this or all of them look like this, we know that that's a regular language. Now, just because I have a grammar that productions don't all look like this or all look like that does not necessarily mean it's not a regular language. It might mean that it could be represented by one of these but isn't. So we'll talk a little more about that in a little bit. All right, so context-free grammars, where regular grammars can only represent regular languages, context-free grammars can represent a broader family of languages, meaning they're more languages than just the regular languages. In other words, regular grammars can define the same things that DFAs, NFAs, and regular expressions define, and only those things. But if I go to a context-free and allow that right-hand side to have more things than just that single variable and the terminals either at the front or the end of that variable, then that context-free grammars can represent, if we relax that, can represent languages that we cannot make with DFAs, NFAs, regular expressions, or regular grammars. So while all regular grammars are context-free, all context-free grammars are not necessarily regular grammars. And some context-free grammars can represent non-regular languages. We'll take a look at that example that we did before in a second. Before we do that, though, if we kind of look at the Venn diagram of the context-free, the family of languages that can be represented with context-free grammars is called the context-free languages. And that's pretty obvious why. Just like regular languages, the family of regular languages define things that could be made with a regular expression. All of the possible regular languages or things that we create with a DFA would be in here. Context-free is a superset of that. In other words, we could make all regular languages with a context-free grammar, but we could also make some that are out here in this gray area, not inside the yellow area. So that creates that Venn diagram that looks like what we have down there. Now, so kind of to recap what we're talking about here, DFA, NFA, and regular expressions can only define regular languages. And I would also add to this regular grammars onto that list. So regular grammars, DFA, NFA, regular expressions can only get us regular languages. But context-free grammars can define all of those, but also other languages that are not regular, that are outside of what we can touch with those. All right, so let's look at a quick example here. And here's an example of in this case, a regular expression. So we know that that regular expression is a regular language, so that means we can make a regular grammar for that. And let's make a right linear version of it for this. So in this case, we have S produces AS, S produces BS, and S produces A. And let's focus on this a little bit. So notice what this was saying up here is this is A or B star. So we can get 0 or more A's and B's, but we eventually have to stop when we get an A. It has to end with an A. So this is all strings of only A's and B's ending with an A. Now let's look at how this grammar embodies this. So we start with S. We could take the production S directly to A, and now we have only terminals, so we stop. So A is definitely in the language. Now what about BA? Well, we could take the one S going to B, and then that calls S again, which goes back to here again, and now could drop out and pick the third one and pick A, so we could get BA. What about AA? Well, we did take this, start with this first production, do AS, and then S to A, so now we have that substituted in there, we have AA. So notice that the way this works is through essentially what would amount to, if you're used to thinking in programming terms, of recursion. So in other words, S can produce either an A or a B, and then followed by S again. And since S is the same thing again, it can produce another A or B, followed by S, which would be another A or B followed by S. And eventually we'd get to the point where it has to stop recursing. And in that case, it would hit this S produces A, and it would end with an A. And notice that matches the language that this produces. 0 or more A's and B's, eventually terminating with an A. So is this right linear? Yes, because all of the productions have a single variable on the left and a string of terminals on the right with a single variable at the end, or just terminals on the right. So this is definitely right linear, which means it's definitely a regular grammar. And in this case, it definitely is defining the same language that we had up here. Now, is there a left linear grammar for that language too? And the answer to that is yes. And the reason being that really any regular language has both a right linear and a left linear grammar that define it. So let's look at the left linear version of this. So here's the left linear version of this. And notice we have S produces AA. This is the A at the end. So in other words, this is saying there's going to be a string of something with an A at the end. That's what we want, a string of something with an A at the end. And now what is that something defined as? Well, I used another variable for that. I used A, capital A. So A can produce either nothing, which would be the case where we just have the A by itself at the end, or it could produce a B or an A with more stuff before that, which could be either a B, an A, or nothing, or more stuff before that, B, A, nothing. And so notice this recurses, but then the only difference between the right linear and the left linear is the right linear is growing from left towards the right. That's why it's called right linear. It's growing toward the right in a linear fashion, always adding symbols on the end, never adding them in the middle, never replacing things in the middle, always on the end. And the other one is growing left to right. So in other words, this is kind of the same process as this. It's just building it from this side toward the A, or from the A backwards toward this stuff, and eventually terminating with lambda. And you'll notice this is definitely left linear because every production has a single variable on the left, and on the right it's either just a string of 0 or more terminals, or terminals at the end, a string of terminals with a single variable at the beginning. And again, with a linear grammar, right linear, left linear, with a regular grammar, you cannot have more than one variable on the right-hand side and only ever a single variable on the left-hand side. Now, there is a more compact notation that I want you to be aware of that you may see looking stuff up on the internet, and that we're going to use from here on out. And that is that if we have something where it's the same variable on the left, we could actually combine those into a single line like this. But this OR here is not the same as the regular expression OR. So this vertical bar says S has a production AS, it also has a production BS, and it also has one A. So this is the same thing over here, but just in a more compact notation. This is more the formal view of it. This is a way to just write it in a way that's a little easier to put in a compact space. So in other words, we're kind of factoring out the S produces and just saying, well, it's either this, or it's that, or it's that. But this is not a regular expression. In other words, you cannot put parentheses around things. You cannot put stars on things. You cannot put pluses on stuff. You can't do anything else other than this string of variables and terminals on this side. And the compact notation for the one down here, notice S we couldn't combine with anything because it only has one production, but A has 3, so we can say A produces capital A, capital AB, and or lambda. And that compact notation we're going to see again later. Now, so that was a regular grammar, or 2 regular grammars that define that regular language A or B star followed by A, that regular expression we have there. Now, what about non-regular languages? And so let's go back to that one that we could not make a DFA for, a regular expression for, or a NFA for. And that turned out to be impossible. We proved that that was impossible. Well, here's a grammar that does it. S produces, and this is for n greater than 0. So S produces ASB. So an A at the front, a B at the end, and eventually, and it recurses and can make another A at the front, B at the end. So in other words, every time I get an A at the front, I get a corresponding A at the end. That's going or B at the end. That's going to make them have the same number of A's as B's, but eventually we have to stop, and what we're going to stop with is just AB, and that's going to make sure that n is greater than 0. So S could take this and have one A and one B, or it could take this followed by that and have AABB, or it could take this twice and have that and get AAA, BBB, and so forth. And the compact version of that is just S produces ASB or AB. And you'll notice that that language could not be touched with a DFA, an NFA, a regular expression. We also can't make a regular grammar for that. But it's easy. It just takes 2 productions to do this with a context-free grammar. So 1 variable, 2 terminals, 2 productions, single defined start state. Really easy to do with a context-free grammar. We could never make a DFA for that. Okay, that's all for today. I want to, before I finish the video though, I want to take a look at assignment 4, which is being posted today as well for you to start on. And assignment 4, you're going to have to write some of these grammars. So I want to take a look at that. I'm going to go ahead and pause this, and then I'm going to set up the document camera and at least do one of those with you here today. So let me go ahead and pause the video. I'll be back in 1 second. Okay, we're back, and I want to bring up the, before I do anything else, I want to go ahead and bring up the assignment and take a quick look at that. So here's the assignment. Let me zoom in a little more on it so you can see it a little better. All right, so the first part here for part 1, you have to find both a left linear and a right linear regular grammar for the language represented by each of these following regular expressions. So in this case, I'm giving you a regular expression, and you have to find a left linear and a right linear grammar for that. So in other words, you're going to find one of each. So there are going to be 2 things you have to do for each of these A through E. Now these are all going to be regular grammars, obviously, because they're going to be 2 regular grammars, one that's left linear, one that's right linear. So I want to take a quick look at that, and I'm going to do one of these with you. And let's take a look at, I don't know, let's do letter A here. So this is going to be part 1, letter A. So let me switch to the document camera for a second. So just give me 1 second here. Okay. Okay, so here's the document camera. Let me make that a little bit. Oops. Okay, so in this particular case, what we're going to do is I'm going to solve that one that we had up just a second ago. Let me kind of try to get rid of the shadow a little bit here. All right, so what the one that we want to do is, let me move this so the paper is top left corner here. All right, there we go. So this is part 1. So part 1, letter A. So for part 1, letter A, the regular expression was A or B, followed by A or B, followed by A or B, followed by A or B. So in other words, 4 characters long symbol or strings consisting of A's and B's. So now we want to have a right linear version. And the right linear version of this, remember what the right linear versions do is they grow from left to right. They grow toward the right. So in other words, the variables are going to be at the end of the string. So we're always going to start with S, and we're going to have S produces. Now, so in other words, the way to think about this is we're going to produce this, and then we're going to follow that with something else. So A or B. So in other words, we're going to have something like A. And notice that one thing to note is by convention, lowercase letters are going to be our terminals, uppercase are going to be our variables. So S can produce AA or BA. So this is corresponding, that A is that B is that. So it has a choice. It could take this one from S, or it could take that one from S. But then it moves on to the rest, which is A this variable a, and then the rest now looks like this stuff here, which is going to be another a, so a, but we don't want to put capital A here because that would allow it to create an infinite number, and we can't do that. We need to have exactly 4. So this is going to be now b, or b, b. So now we have those two taken care of, and now c is going to be this part, or let's do capital B, I mean, b, and that's going to be a, c, or b, c. So this is the first A or B, this is the second A or B, this is the third one. Now all we have left for C is either A or B. And so there's my right linear version of this grammar. Now there are other ways to maybe write this as well, but notice, well, first off, let's check, is it right linear? Do we always have a single variable on the left-hand side of all the productions? Yes. On the right-hand side, do I have a string of 0 or more terminals ending with a single variable? Yes, 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 yes. This doesn't have a variable, but that's okay because the other option is just a string of terminals with no variable. So this is definitely right linear. Now, how are we going to do the left linear version? Now the left linear version, we're still going to have to start with S, but now we're going to have that because the variable's on the other side. So in other words, rather than starting with this one and then saying it's going to be an A or a B followed by something else, which is going to be an A or B followed by something else, we're going to have to say this is going to end with an A or end with a B with something before it. So in this case, I'm going to put A before it. So this is now the last symbol where this was the first symbol. And this might look like we just took these and we flipped them all, but there's some languages where that's not going to be the case, where these just flip. So for example, if this didn't start with an A or have the same symbol as that, these would not just be those switched. So this is representing the symbols at the end of the string. This is representing the symbols at the beginning of the string. But now what is this A here? That's what comes before that. So in this case, this is going to be BA or BB. And then B is going to be CA or CB. And then finally C is just still going to be A or B. And this one turns out that these look like you just take these and flip them, but that's not necessarily the case. It depends. That just so happens that because this has an A or B at the front and that's an A or B at the end, those are the same. It turns out in this case that that's what we end up with. So in this case, that is essentially what we need to do for all of the rest of that assignment. Let's switch back to the assignment quickly here. All right, so back to the assignment here. You'll notice that that's what you're going to do for A, B, C, D, and E. So everybody should get at least part 1A, right? Part 1B is a similar thing. You're going to create an A, B, and you can have two symbols together. So this one, if you're doing the right linear, you'd say, all right, S produces AB followed by the rest of the stuff. And what's the rest of the stuff? Well, this is going to produce 0 or more A's and B's, and then eventually that's going to move on. When that moves on, it's going to have to produce just BA and then stop. So think about that, each of these, how you do both a left linear and a right linear version of all of these, and see what you can come up with. All right, part 2 is we're finding not left linear or right linear, but just context-free grammars in general. So in other words, context-free means a single variable on the left-hand side, but the right-hand side can be any string of zeros or ones. Now notice that in this case that A to the N, B to the M, where N is equal to M, that's one we did before, but this one doesn't have the stipulation of N greater than 0. So this could equal 0. So in other words, lambda should be in this language. So think about how you would take the one we did in the slides previously in the lecture and how you would make it so that we'll also accept just lambda in addition to what we had in that. And this one is all strings where they don't match, where the number of A's is different than the number of B's. So this is kind of the complement of this one. So any string that it doesn't match, and the complement use it in what we're doing with grammars is actually a little more complicated than the complement was with DFA. So we have to actually think about how to create this. But one way to think about creating this, if you think about how do I make it so the string of A's is always a different number than B's. And the way to think about that is, how would you make sure a scale is unbalanced? Well, if you balance it and then add more to one side, or add more to the other, but not to both, then it's guaranteed to always be unbalanced. In other words, make an equal number and then either add more A's, or make an equal number and add more B's. So think about how to do that. And the rest of these, I'll let you puzzle through that. One word of explanation here that's probably important to look at is this W raised to the R. That's reverse. So this is all strings that have an even number of characters that read the same forwards as they do backwards. In other words, this W part at the front might be AB. That means WR is that AB reverse, so BA. So AB, BA would be in this language. AA would be in this language. AA, B, BAA would be in this language. So this is the reverse of, the second half has to be the reverse of the first half. In other words, they're going to be palindromic. They're going to read the same forwards as backwards, but they also have to have an even number of characters. And now part 3 has a couple of proofs. And we did a proof like this a couple lectures ago. A to the N, B to the M. This is where they're not equal. So I want you to justify, is that language regular or non-regular? And I want you to provide some sort of proof that justifies that. If I were you, I'd use that template for the one we did in class, but think about how them not being the same number would be different from that one. And then there's a second proof here that I want you to do. I want you to justify if this is true or if this is false. And the statement is, if L1 is a non-regular language and L2 is a language such that L2 is a subset of L1, then is L2 also non-regular? So in other words, is a subset of a non-regular language always guaranteed to be itself non-regular? And if it's true, I want you to prove it. If it's false, I want you to provide something like a counterexample or some sort of other justification. I want you to convince me if it's true, or convince me if it's false. All right, it turns out that these shouldn't be too complicated to do. There's only 2 of those. But basically, this assignment, unlike most of them, is actually worth 30 points instead of 20. And the main thing to keep in mind here as you go through these is that make sure you cover any, all, and all strings that are in that language and don't include any that are not in that language. So in other words, we want all of the possibilities where a string of A's followed by a string of B's is equal. All of the possibilities where a string of A's followed by a string of B's is not equal. Every one of them. And so just make sure to think about it that way. And we will do that. So if you have questions or problems, let me know. Otherwise, we are done for today. So that's it for today. Everybody stay safe. And somehow my screen changed sizes, so you can't see which slide number it is, but I'll fix that later. But anyway, stay safe. I'll see you soon. And what we're going to do next class is we're going to talk a little more about these grammars and how you can tell if a string belongs to that language of that grammar or not. And notice the grammars can be a little more complicated to look at, a little more complicated to think through, but they help you with thinking about recursion. And one of the cool things about grammars is that they are used for defining structures like you would see in programming languages. In other words, you can have an if statement that has if statements inside of it, that has while loops inside of the if statements, and a while loop can have if statements inside of it. Or even an expression, like you have multiplication and division, and you can have that in parentheses and then add that to something else that's in parentheses and then raise that to some power. That itself is recursive in its design. And notice that recursion in context-free grammars is very natural. S produces this thing that has an S that then goes back and does that. So it's very easy to define programming language specifications using these context-free grammar kinds of things. And in fact, let me show you one more thing here. I'm going to pause for a second and show you. Okay, the last thing I wanted to show you is I searched for BNF Python. BNF is a form of context, a way of writing out a context-free grammar for a programming language. And notice that part of the documents for python.org is the full grammar specification for the entire Python language. If I click on that, here is the entire specification for that with all of the productions that make the Python language work. And you'll notice it's really, it looks fairly long, but it's really not as long as you would think it is. This is all kind of written out. But you'll notice that at the top, you have this thing, you have a file. And a file consists of this statements thing, and then what's called an end marker, which says that's the end of the file. And then what do statements look like? Well, if we go down here, statements consists of statement plus. This is BNF. This is actually what's called an eBNF grammar that allows us to have things like plus inside of here. But then a statement. What's a statement? It's either a compound statement or it's a simple statement. What's a simple statement? A simple statement is this exclamation mark, semicolon, new line, and then semicolon dot start statement plus. What are the statements? What does statements look like? Well, here's what is a compound statement? Compound statement, new line. What's a statement, new line? It's a compound statement, new line, simple statement. This is just a grammar. This is a grammar. Notice that, for example, here's an augmented assignment operator. They're all listed there. It's either that pattern or that pattern or that pattern. And this is the entire grammar for the whole language. What's an if statement look like? Well, the word if, followed by a named expression, followed by a colon, followed by a block, which is an indented code underneath that, followed by an else if statement or an elif statement, or it's an if statement, named expression, block, followed by an optional else block. Well, what's an else block look like? It's an else, colon, and then a block. And what's a block? Blocks are defined in here. So this is this is the entire grammar for Python. We could also search for, if we wanted to, let me search for the BNF C language. Here's the syntax for C language. Notice this is a much shorter grammar, but this is the entire grammar for C language programs written out in this BNF format. There you can see assignment operators are one of these. Statements are either a labeled statement, an expression statement, a compound statement, a selection statement, an iteration statement, or a jump statement. What's a labeled statement? Well, a labeled statement consists of an identifier, a colon, and then a statement. And that recurses back up to here. And so you'll notice that this is a direct use of those context-free grammars. So now I promise I'll stop. No more things. You've gotten used out of the habit of, or maybe I have not been doing one more things as much as I have in the in-person labs or lectures. So I had to do a couple of them. But let's go ahead and stop there. Let me switch this back to the slides to have a nice clean finish. So that's all we're going to do today. So everybody stay safe and start on that lab 4. See what you can get done on that today. If you have any questions or problems, let me know. And I'll be happy to answer them. I'll see you next time.